Hello and welcome. My name is Elhelw. In a previous video, I talked about joins being one of the most important operations in relational databases. Today, I will talk about another very important operation, and that is aggregation. What is aggregation and what is it used for? We're going to see together in this video. So aggregation is an operation that we use to combine and summarize multiple rows and produce a single result. So it would look something like this. So starting with this table, we can combine some rows into a single value, combine another group of rows into another single value, combine another group of rows into a value, and so on. So why do we do this? Usually when we're dealing with data in a database, we're dealing with huge amounts of data. We have large data sets that we would like to analyze, that we would like to get insights from. So it is very useful to have something that will allow us to condense this data or summarize it in a way that makes it more manageable and easily understandable or easy to analyze. Often when we do this kind of operation, we would produce some kind of, again, summarized information that will give us meaningful insights into the data. You will often see queries that are looking for, average of something or minimum or sum or something like that. So this means that you don't need to look at the individual data, but you want to look at these aggregated or summarized information. This is another way of saying that this is a way to simplify our data and simplify our analysis that we can do on the data after that. Because the analysis, instead of having to deal with all the individual rows, now it has to only deal with these summarized information that is produced by the aggregation. This is often something that is used in analytical systems, BI or business intelligence tools, data warehouses, and so on. So, okay, what does that look like in practice? Instead of the empty table that we showed earlier, let's talk about a real table with real data. So here's a sales table. It has some information about sales of certain items. So each item, the category in which this item belongs to, the date of the sale, and the amount for which it was sold. So one potential query would be, okay, we want the total sales amount per category. So for each of the categories, we want to see how much sales amount was sold for this category. So in SQL, this would look something like this. Select category and sum of amount as total from sales group by category. So we're grouping by these categories, and for each category, we want to get the sum of the amount. So if we apply this query, it will give us data that looks like this. So we have all the categories, and then for each category we have this total. We could try to summarize it even more if we want to get just the whole amount of the sales, not broken down by categories. So we could say, okay, actually select sum as total from sales, don't group by anything, just give me the sum, and it would be a single value. So this is showing how much we can summarize this data and how many levels of summarizations we can have. Another example, we can say, okay, this is the order table. It has different orders. Each order has its date and the customer that made this order. And we want to get how many orders per customer do we have. I don't really care about the dates. I don't care about amounts. I only care about the number of orders in this case. So the query would look like this. And this is the output that we will get. Each customer with the number of orders associated with that customer. Another example would be, okay, I actually don't care about the number of orders. I just want to see a list of customers, right? So basically just list all the customers that we have. Obviously, when you're asking for a list of customers, you don't want to see each customer multiple times. Just want, a duplicate-free list. So this will look like this and will give us the list of customers. In this particular case, we also wanted it to be sorted, so we added the order by at the end. You could also express this same query in a different way. You could say select distinct customer from the table, order by customer. So either group by or distinct can be used for duplicate elimination. So far, the queries that we've seen were operating on the table as a whole. We can also have queries that have certain filters on them. So you could say, okay, I want the sales amount per category, but I want this only for the sales that happened in the year 2022. So the query would include a where clause that filters by the year part of the date, and it has to be equals to 2022. So anything that does not satisfy this will not be part of the result. So the two rows here that have 2023 and 2021 will not be considered, and then the rest of the rows will be aggregate it as we did before, and we'll get a result that looks like this. On a high level, each of these aggregation operations can be split into two main phases or two main steps. The first step is figuring out the groups, understanding which rows belong into which groups. This is usually the case when we specify a group by or a distinct, as we've seen in previous queries. So when you say group by category, for example, then each category is a group. When you say group by customer in the example with the customers and the number of orders per customer, so each customer is a group. So all the rows that belong to that customer should belong in that group. The same thing with distinct. So when you say distinct customer, for example, then again, each customer is a group. If you don't have group by and you don't have distinct in the query, then the whole table is a single group, which is what we've seen in the very first query when we just selected the total without grouping. So there was treated the whole table as a single group, and we produced a single value. Whether we have a single group or we have multiple groups, the next step is combining the values within each group. So we combine the values using some of the aggregate functions that we've seen, things like count, min, max, sum, average, stuff like that. And then the output of that becomes the single value for that group. In some cases, you may not want to use any of those. In the case of duplicate elimination, for example, so you're just outputting the grouping key and that's it. So again, the main steps are the splitting into groups and combining the values within each group. Let's see what that looks like with an example. So here is the query that we've seen before, getting the sales amount per category. Let's illustrate the groups or the steps that we've just mentioned. Again, this is the query that we have. Category here is the grouping key. So the first step is to split the table into separate groups based on this grouping key. So you can visualize it like we have these, barriers, and we've grouped all the rows that have furniture into one group, all the rows that have electronics into one group, all the rows that have kitchen into one group. How do we split those groups? We're going to see that later on. But once we have split those groups, then we look at what we want to output. In our particular case here, we want to output the sum of the amounts. So we call this the aggregate function. So now for each group, we want to apply this aggregate function on the data that we have. So here we're applying it on the amount column, and we're going to produce the sum. So for each group, we're going to produce the grouping key plus the output of that aggregate function. Let's see another example. This is the example with the duplicate elimination. So we just want to list all the categories. We don't want any other information. And as I said, you can also write this query using select distinct. So we have our grouping key here. First step is to split the table to groups based on the grouping key. So same as the last example. Furniture group, we have the electronics group, we have the kitchen group. And then since we don't have an aggregate function here, we just want to output the category for each group. So the output is going to be furniture, electronics, and kitchen. That's simple. So basically here we don't have the second step of doing some kind of, combining data. So with that in mind, we can see that the main challenge that we have to deal with is figuring out how to split the table or the input into these separate groups. The groups, as we said, they are based on the grouping key, whatever we have in the group by clause or whatever is after the select distinct. So for each group, all the rows that belong to that group need to have the same value for the grouping key. As an example, again, the category, all the rows in the electronics group need to have electronics in the category, and so on. So what we want to do is we want to find all the rows that have the same value in those grouping keys so that we can create those groups. How do we find all the rows that have the same value? Let's take a step back. If you've watched the video about the join algorithms that we had before this, you'll start to notice some parallels between the joins and the aggregation. Specifically, I'm talking about equijoins. So equijoins, you're trying to look for things that are equal, right? For equijoins, you're trying to find rows that have equal join keys across two tables or across two inputs. In aggregation, we want to find the rows that have equal grouping keys from within the same table. So there is some similarity here. How do you find things that are equal, whether in different tables or in the same table? To find things that are equal, usually in databases, there are two ways to do that. You either use sorting or you use hashing. Why do you use these two things? When you sort something, then all the equal values are right after each other. when you hash something, then all the equal values end up in the same bucket. So it's easy to find them in both cases. We've seen that with join. When we did the join, we had a sort-based algorithm, which was merge join, that sorts the inputs, and then now we have all the values that are equal. It's easy to merge them. We've also seen hash join, which uses hashing so that all the values that are equal end up in the same bucket, and again, it's easy to join them. Same thing is going to happen with aggregation. We're also going to have a sort-based algorithm and a hash-based algorithm. Why only hash and sort? Why not have something like nested loop join, for example, but for aggregation? I mean, you could. You could have something like a nested loop, so two loops looping on the same table and then finding all things that are equal, all different combinations. Of course, this is not very efficient. As we've said in the join video, nested loop join is the least efficient algorithm, and it's the one that we try not to use unless we have no other alternatives. Usually it's useful when you have non-equijoins, so things like less than or greater than. We don't have that with aggregation. With aggregation, you just want to find things that are equal, so you only care about equality. So the one case that was good for nested loop join, we don't have that here, so then we don't have something similar to that. We only focus on sort and hash. So let's start talking about the sort-based aggregation first. We're going to explain with an example and then see what we can find. So again, this is the same query that we've seen before, the duplicate elimination query. We just want to list all the categories, all the unique categories. So the query could be written in one of those two ways. The grouping key is the category. This is our grouping key. The table is not sorted right now. So the first step is to sort the table by the grouping key. So we produce something like this. You can see all the similar values are now right next to each other. So the next step is to do a pass on that table to scan it. So now we are on the first row. Look at the category. It's electronics. We're going to output that. Basically, the idea is that we're going to keep track of what is the last row that we've seen. So when we go to the next row, electronics, this is the same as the last row, so we know that we've already output that value, so we don't need to do anything here again. We go to furniture, this is not the same as the last value. So this is a new value that we haven't seen before. So we're going to output furniture. Same next time, this is the same as the last value, so nothing new. Here we have a new value that I haven't seen before, so kitchen, we output that. And when I say we haven't seen before, we're only comparing to the previous row. We're not comparing from the beginning. Because the values are sorted, it allows us to make that comparison and guarantee that once we've passed that range, we're never going to find those values again. Again, here, kitchen, it's the same as the previous one, so nothing new here. And then we've reached the end of the query. So putting the categories in order allows us to make sure that whenever we're within that same value, we're just going to output it once. Once we pass that, we're going to output the next one, and so on. So the result will be the unique list of categories. Let's see a different example. Here we want to output the category plus the sum of the amounts for each category, right? So it's not enough that we only output the category names, but we want to do some processing on the amount information. So again, the first step, sort the table by the category, which is the grouping key. Now, as we do our scan, we're going to have to maintain some additional information, as we will see shortly. So first row, category is electronics, and the amount is 80. We're going to keep track of those on the side. So the key is electronics, and the sum so far is 80. Again, we know that all the electronics rows are right after each other. So as long as we see rows with electronics, we can keep adding to that running sum as we go. So we see the next row, it's also electronics. So we're going to take that new value and add it to that sum that we have. So it's going to be 880 so far. Now it's a new value, furniture. This means that we have finished the electronics group. And we know for sure that we're never going to find anything else that says electronics. So we know we're done with that. So we can output anything that has to do with electronics. And we can replace the values that we're keeping track of to reflect the new group. So now it's furniture, and now the sum is starting with the amount of 300. So we're going to repeat that for every row. Every time we are within the same group, we're going to add the new values. Once we transition to a new group, or once we reach the end of the table, we're going to take the values that we have, output it, and then put the new group in its place, and so on. So by the end of the table, the output will look like this. We have seen that for the sum, we needed to keep track of this running sum, right? For every aggregate function, we need to keep track of different information. So these are some of the most common aggregate functions that you'll ever see: sum, count, min, max, average. There are lots and lots of other aggregate functions, but these are probably the most common and the most used ones. So what do we keep track of when we're applying these functions? For sum, as we have seen, we keep adding the new values that we have to the running sum that we are maintaining, as long as we are within the same group. If the query was looking for a count, then basically each time you find a new row, you just need to increment the counter with 1. If you're looking for a max, then you are maintaining the maximum value within the group. So every time you find a new value, compare that to the maximum that you have so far. If it's greater, then replace it or override it. If it's less, then leave the maximum as is. And of course, the opposite with minimum. Average is a little different because you need to maintain two pieces of information, not one. You need to maintain the sum and the count, because average is sum divided by count. You cannot just maintain an average and then each time average the existing one with a new value, because that will give us incorrect result. So we need to maintain both the sum and the count. So every time you find a new row, you add the new value to the sum and you increment the count with 1. And then when you reach the end of the group, or when you go to the new group and you want to output the data, then you make the division. You divide the sum by the count and you output that as the average. Okay, so as we have seen, the sort-based aggregation, the first step that we were doing is sorting the table, right? So before we start scanning, the table needs to already be sorted. Of course, sorting is expensive, so we would like to avoid that. Usually the optimizer will only use the sort-based aggregation if the data is already sorted by the grouping column. When would that happen? There are many cases. For example, if you are just scanning an index, for example, if the index happens to be on the grouping column and you're scanning that index, this means that the data is sorted by the grouping column. Then you can use the sort-based aggregation. If you are coming out of a merge join, for example, which was joining using the same column as the grouping column, then you know that the results of the join is sorted by that column, so it can also be used for sort-based aggregation. So there are different operations that output the data in a sorted order, and if that order matches the grouping key, then you can use the sort-based aggregation. Also note that when you use this sort-based aggregation, the output is still ordered using the same grouping key, as we've seen in the previous examples. So this could be also the input to another operation that depends on that order. What if the data is not sorted, right? So we said that we use sort-based aggregation when the data is already sorted by that grouping key. If the data is sorted by something else, or if it's not sorted at all, then we cannot use this. So in that case, we are going to use the hash-based aggregation. Hash-based aggregation is usually cheaper for non-sorted data. And hash-based aggregation, like anything that's hash-related, it uses a hash function and a hash table. So let's see what that looks like with an example. Again, our duplicate elimination example just lists all the categories. So first thing, we're going to start with the hash table and the hash function. We're going to use those to split things into groups. So what we're going to do is that we're going to scan the table, go over all the category values for each row, for each one, hash it, and put it in the hash table. So starting from electronics, apply the hash function to that. The hash function will tell you which bucket to put it into. So we're going to put that in the corresponding bucket. The next one, furniture, hash function is going to tell us about the bucket. We're going to put it there. Same thing for kitchen. Now we see furniture again is going to go to that same bucket that we put furniture before, so basically nothing new. Kitchen, same thing, we've already seen that before. Electronics is going to go to that same bucket, so nothing new there. So all we need to do after that is just scan the whole hash table and output the keys from there into the result. So this will give us a unique list of categories, which is what we want from this query. Notice that the result is not sorted by anything, because obviously the hash table does not have any sort requirements on it. So yeah, there is no order here. Second example, we want the categories, but we also want some additional information. in this example, I replaced the sum with average just to see how average works. So for each category, you want the average amount of sales. Might not be a very realistic example to something that you would want in reality, but just to illustrate how average works. So again, we have our hash table and hash function. First row, electronics. Now we're putting the key, but we're also maintaining other information as we mentioned before. For average, we need to maintain both the sum and the count. So sum is going to be the running sum of all the amounts that we find. Count is going to be the number of times that we find this particular category. So to start, sum is going to equal to 800, which is the value of the amount, and count is going to be 1 because this is the first time that we see this. Now furniture, again, it's the first time that we see it, so count equals 1, sum equals 120. Kitchen, first time we see it, count equals 1, sum equals 350. Now the next time we see furniture, we're going to know that we've seen that before. So we need to update the information that we have. So we add the new amount to the sum that we had before. So we already had 120. We add 300 to that, so that becomes 420. And we also increment count, because this is the second time that we've seen furniture. Same thing for kitchen, we update the count and the sum. Same thing for electronics and so on. So every time we find a category, if it's new, we're going to add a new entry in the hash table. If it's something that's already existing in the hash table, we're going to update that entry. And then at the end, we're going to scan the hash table. For each category, we're going to divide the sum by the count to give us the average. And this will be the result of the query. So the way I'm explaining this is just explaining the things, how it works in theory. When you go in practice in actual database engines, there might be some other considerations that you have to look at, like the size of the hash table, the size of your memory, whether the hash table can fit into memory or not. You might have to split the hash table into multiple partitions and bring one partition into memory at a time. So in those cases, you might see that in the literature. Maybe you might see that sometimes they use 2 hash functions instead of 1. So first hash function to tell you which partition you need to deal with, and then the second hash function to actually go to the bucket, as we have seen here. So yeah, there are some deep level details that you can find in other places, but today I just wanted to explain the algorithm, how it works, without getting into these hardware based or system details. All right, let's demonstrate what we talked about on Postgres to see the 2 different kinds of aggregation that we've discussed, and also see when will the optimizer choose each of them. So let us start by showing that table that I defined here, sales table. It has 3 attributes, region, product, and revenue. And it also has 1 index on the region column. Let's see how many rows we have there. Okay, so with that, let's try a simple aggregation query. So basically, I want to select each region and the sum of revenue for each of those regions. So let's see what the plan looks like. Here we have a hash aggregate. So this is the hash-based aggregation. And below that, the input to that is a sequential scan on sales. This is expected because we did not have any sorted data in this case, so that we have to do a full scan of the table. The table obviously is not ordered by the grouping key, so we can only use the hash aggregate in this case. If we were to use a sort-based aggregate, then we would have to add a sort operation, which would be too expensive. So the optimizer chose to use the hash-based aggregation. Let's try to do basically again the similar query, but we're going to remove that sum of revenue. So basically now we're only looking for the region values. So this is the duplicate elimination query that we've seen earlier. Same thing, it's still going to use a hash aggregation because of the same reason that we said before. Still, it has to do a full scan of the table, and the table is not ordered. Of course, the estimated cost here is a little less because it doesn't have to do the summation. So that's why this is less than the first query. We can also write this query in a different way, as we've seen in the slides, using the select distinct. So I could say select distinct region from sales. And again, we will see it's the exact same plan as before because these 2 queries are equivalent. And even the cost is pretty much the same. All right, let's try something a little different. So let's go to that first query that we wrote. And let me add a condition. So I'll add a where clause where region equals to east, for example. And let's see what happens here. So now we do not have a hash aggregate. We have this group aggregate. Group aggregate is Postgres version of the sort-based aggregation that we talked about. So whenever we see group aggregate in the plan, we know that this is the sort-based aggregation. So why did it choose the sort-based aggregation this time? Because I had this condition, and because we have an index, if we go up there, we have an index on the region column. So we could use the index to look for the rows that have regions equals to east. This condition also happens to be the same column that is used in the group by clause. So this is the grouping key. Using the index means that we'll get the rows back sorted by region. So if they're already sorted by the grouping key, this means that we can use a sort-based aggregation. So let's look at the plan. We have, starting from the bottom, we have an index scan. So it's going to scan that sales region index using this condition. So region equals to east. This will return the regions with the row IDs that contain those values. But because we need the revenue value, this is not in the index. The index is only on the region. So we need to get this from the table. That's why we need to have this heap scan on the sales table to get the revenue values. And then the data is sorted by the region, so we can do the group aggregate, which is a sort-based aggregation, and produce the result of that query. Let's try to change this query a little bit just to show something different. If I were to say, for example, instead of sum of revenue, I would say select count star here. Now, we still have a group aggregate, so still the sort-based aggregation because of using the index, because of this condition. But now notice that we have an index-only scan. Index-only scan, if you remember the video that we had on indexes, this means it's a covering index, because all the information that we need for the query is actually in the index. We only need the region column and the number of rows that it has. So as it scans the index, it can just count how many rows have that region value. So it doesn't need to go to the table at all. This is why it does an index-only scan. So just an interesting thing to see how these different things work together. All right, so to summarize what we've talked about today we were talking about the aggregation operation, one of the most important operations in relational databases, specifically for analytical workloads, data warehousing, business intelligence tools, and so on. Things where we're dealing with huge amounts of data and you want to summarize this data to be able to get some insights from that data. So for that purpose, to use aggregation. Aggregation combines multiple rows into one by applying certain functions or certain computations on groups based on the grouping keys that we have in the query. We talked about two different algorithms for aggregation. We talked about a sort-based algorithm and a hash-based algorithm. The sort-based aggregation is best when the data or the inputs are already sorted. This could be for a bunch of different reasons, as we've explained. The data is also, the outputs of that operation also tend to be sorted by the grouping key as well. If the data is not sorted, then we use the hash-based aggregation, which employs a hash function and a hash table to determine which rows belong to the same group. Hopefully this clarified the aggregation and how it is implemented, what the different algorithms are. If there are any questions, please add them in the comments. Otherwise, please hit the like button, subscribe to the channel to get all the updates. And with that, thank you so much for watching, and I will see you in the next video.